A very good morning to our tutor. My name is Chong Matrix number X60216135343 or 1 for the course Bachelor of Science in Project and Facility Management with honors. I'm studying in Kuting Learning Center for semester May 2020. Today I would like to present for the subject for EBCT 3103 Construction Technology regarding for Building Information Modeling BIM. Let's study about the history for the how is the BIM become today. Computer-aided design CAD technique have been in use by the construction industry since the early 1980s. The next paradigm shift was the introduction of building information modeling BIM in the field of architectural engineering and construction in the mid-1990s. What is building information? Building information modeling is is a process supported by various tools, technologies and contracts involving the generation and management of digital representation of physical and functional characteristics of places. Building information models are computer files, often but not always in proprietary format and containing proprietary data, which can be extracted, exchanged or networked to support decision making regarding a built asset. BIM software is used by individual, businesses and government agencies who plan, design, construct, operate and maintain building and diverse physical infrastructure such as water, refuse, electricity, gas, communication, utility, road, railway, bridge, ports and tunnels. In Malaysia, BIM implementation is targeted towards BIM Stage 2 by the year 2020, led by the Construction Industry Development Board CIDB Malaysia under the Construction Industry Transformation Plan CITP 2016 to 2020. It is hoped more emphasized in technology adoption across project life cycle with induced higher productivity. How BIM can contribute to the development of smart built environments during the post-construction management of a facility. BIM is a methodology enabled by a set of software, tools and processes for facility in the creation and use of the digital representation of the physical and functional characteristics of a facility. In terms of software, BIM introduced actionable information format. For example, International Foundation classes for modeling and visualization building entire in 3D in terms of process. BIM facilitated the conveyance of building information from the design phase throughout the building life cycle, supporting cost management, construction management and facility management. BIM also as a methodology has been focused on the following two areas. Number one, development of software tools and techniques for creating and elevation new BIM artifacts that arise as building design and technology involvement. And second is the application and usage of BIM process across the life cycle of a building from pre-construction design to post-construction facility management. The aspect of information communication technology, ICT, is the construction and management of emerging smart built environment. So recent rapid advance in information and communication technology, ICT, have led to their pervasive use across industry sector, including building, construction, and upcoming and important aspect of ICT use that we anticipate to take a central stage is the construction and management of emerging smart built environment. Here, smart built environment refer to a built environment that has been embedded with smart objects such as sensor and actuator with computing and communication capability, making the environment sufficiently smart to interact intelligent with the support their human user in their day-to-day activity. So BIM in smart built environment. BIM hosts the collaborative architectural information and provide the semantic knowledge of the building. With the emerging of smart built environment technology, BIM should be further developed to be capable of seamlessly integrating smart object in building design, verifying the SBE design and feeding smart object with relevant building related information. Designing SBE with BIM is both advantageous and convenient. Firstly, designer of SBE can utilize the building knowledge of BIM for planning the layout of sensor, like actuator and meters. The performance of smart object can be verified against non-constraint and their layout optimized for the best functional performance. Secondly, BIM also serves as a data repository for the physical information of smart object for maintaining and asset tracking in the building post-construction phase. The hardware information of the smart object can be recorded and their installation location can be documented and visualized in 3D. On the other hand, BIM provided a perfect ontology database for SBE. Smart object may be designed and manufactured by different vendors. The data they may provide may vary in structure and they may communicate using different protocol. Middleware is a popular approach to addressing such issue with heterogeneous smart object with the BIM. Each smart object can be profiled through its information exchange interface because BIM is standard compliant. The middleware can extract data format of smart object and other building information for viewing as ontology database. So this is summarized that the BIM in smart building built environment. So we're starting with a smart built environment design and produce design verification, device profiling, information exchange interface in the BIM. The input become the output become a facility management, energy management, then called as smart built environment post construction. So this is the raw building information modeling BIM in smart built environment SBE. So the case study, I have choose 4 buildings as my assignment case study. For the number 1 is the Beijing 2008 Olympic Stadium. 2000 Beijing Olympic Stadium is designed by architect Herzog de Meuron, engineering consultant by Arup UK, main contractor from China Architectural Design and Research Group, and the beam constructor is MTech Jerry Technology. So the stadium is conceptual by the Bird Nest. It's built by in year 2003. Then they've been used for the 2008 Beijing Olympic. So in the beam, the bridging the gap between concept and reality, this is how the virtual and the beam produce the virtual reality. So it's become a modeling concept, design and development details. So the beam model application produce a master model. From the master model, we can see 2D and 3D integration, system engineering and detailing, BOM management and reporting, on-site data and manufacturing data extraction. So the structural beam design also can be used for the beam. So we can see that how the line and the erection of the structure, how it will build in 3D, and the shape of the building, how it will be built. So it's also using the staircase design with 3D, the staircase design in 3D. So this is how it will be looked after the construction of the staircase. So the 3D navigation is allowed to us to see how is the Birdnet Stadium will be look like in 3D. For the case study number 2, I chose Swell Properties 1 Inland East. Okay, 1 Inland East is owned by Swell Property. The total site area is 109,900 square feet, comprising about 54,800 square feet from the site of the industrial building and 55,100 square feet of adjoining land. The approved floor area is about 1.5 million square feet, also proximate to 141 square meter, represent a plots ratio of approximately 14 on the total site area. The approval plan are for a building of 7 story, where 59 office floor to be erected on the site of the industrial building with a height approximately 280 meters. So the estimate construction cost is approximately Hong Kong dollar 3 billion. So the project is completion by in year 2004 to 2008. The consultant architect is by Wong Ouyang, structure by Arup, MEP by Bernhardt, QS by Levitt and Bailey. Main contractor is from Gammon Construction. The project mission is to achieve the defined high building quality grade A and the highest commercial building in the East Hong Kong inland, early to start up the offshore procurement, reduce the construction time, where 7-story building completed in 18 months. So the beam data structuring is integrate the architecture, BS engineer and structural engineer from every floor. For example, this is the tower, then this is the view, the floor plan, and the plan and the 3D will be look like. So the mechanical, electrical, plumbing design, this is a design collaboration to be looked into the building. How is the part line will be go through inside the building. So integrated beam model. So it also can be used for collision checking for the building. Okay, for collision, okay, there is a virtual construction facility study. So this is how the building in a virtual reality before its construction become a physical. So it's a comparison, 4-day cycle in typical flow, revolve work combination and resource utilized across in different base. So it's a comparison we can between reality versus virtual day one. This is day one. This is how is the building been erected. So the reality in the day four. So the progress is approximate like what have been designed in the beam compared to its physical completion. For the case study number 3 is a Guangzhou International Trade Center. Guangzhou International Trade Center is been completed in 2008. So the developer is by Namfeng, China. International Trading Exhibition Center with 17 floors. So the first to fourth floor is the exhibition hall. Fifth floor is the dining area. 6th to 17th floor is a showroom office. So underground will be in first and third floor, consisting car park and shopping area. So the location is Guangzhou, China. So the ground area is 24,862 square feet. The developed area is 132,519.5 square meter. So the architect is a local architect from the Guangzhou Architect Design Institute. So the main contractor is of Shanghai Construction. So it's a Katia beam models is another software that is also can produce the beam. The project mission is improve building quality, reduce construction cost and time, including improve facility by project leadership into information development by the extended building team. Second is improve coordination of building system to identify and address potential conflict. Third, security of construction cost and time to project completion. Fourth is an integration between design, documentation, and fabricator construction activity. Number fifth is reduce project transaction costs like paper printing and rework and etc. So the contract correction of major design fault before construction, early use of building design asset. So this is a multiple view of beam model on the right side, left side. So it's a 360-degree view. So the architecture, structure, MEP view. So this part will be construction first, then the erection for this bay, for this portion. So the architecture and structure design conflicts. The structural beam is above the slab. Okay, inside the beam they detect the beam will be built on the slab. So this is the error. So from the beam they can check it, the error. So the beam will be not construction. So they will be move it. They will do the amendment design so that the slab will be not on above the beam, so that the beam will not be above the slab. So false ceiling height issue. So LO4 after install, the MEP service, the false ceiling height cannot match 3,100 mm. So from here, this is a lack of the ceiling height. So from the beam they have detected it, then they can see the height is not enough for the installation of the pipeline. So it can be amended so that in the physical side there will be no error will be happen. So its original false ceiling height is 6,600 mm. The outcome is 5,500 mm. Which means the ceiling height is not enough, because the outcome is less than the original one. The original one there is supposed to be 6,600, but the outcome is 5,500. So it's been less about 1,100 mm. So the pipeline cannot fit in. So the MAP cannot fit into the shielding. There's a early detection through the beam. So the headroom clearance checking. So this is how all the MAP will be installed in the shielding level, so they can detect it, whether the height is sufficient for the installation of MAP or not. So this is designed for the safety by beam. Okay, virtual reactivity. This is a firefighting pipeline. This is a water-based pipeline. So the difference between virtual and real is virtual they are not designed for the bracket to hold the pipe, but in real one they have the bracket to hold the pipe. So this is will be like kind of reduce the current and also increase the ceiling height. So this is will be looked into the virtual and real reality into the dimension. So this is air conducting. So how it will be installed inside the shielding. So this is the construction of the structure, how it will be erected in 3D way, and then versus the actual one. So it also can be used for 3D navigation. So case study number 4 is a South Pole North Residential Estate. So South Pole North Residential Estate is owned by Bright Strong Limited. Location is DD107 South Pole North, Kam Tin, Yolong, NT, Hong Kong. This is in Hong Kong also. So the project manager is Sun Hang Kai Real Estate Agency Limited. Architect is from Ronald Lu Partner, Hong Kong Limited. CNS and M&E is from Sun Hong Kai Architect and Engineers Limited. So the site area is about 175,977 meters square. So the usage is for residential. So the consisting of the building is they have 36,000 meters square for domestic, 10,000 meters square for non-domestic, and 2,000 meters square for clubhouse. And the building is built in year 2012. So the project mission is to improve visibility by the project leadership into information developed by the extended building team, early use of building design asset, improve coordination to building system to identify and address potential conflicts, for feasibility of construction cost and time to the project completion. Number 5 is integration between design documentation and fabrication or construction activity. 6, reduce project transaction costs like paper printing, rework, and etc. 7 is correction of major design fault before the construction. So testing the work sequence in 4D before the work begins. This is to calculate the cycle time. So excavation, ELS design review, delivery podium. This is optimized of pipe work layout. This is how they save the space. So optimize the headroom before pipe work installation. Easy rerouting of various service to validate alternative routing. Easily checking pipe work arrangement on facade wall. Optimize the wall opening to facade wall. Optimize the pipe work layout in order to avoid the obstruction to the scene view from inside. So this is a mechanical, electrical, plumbing services in podium. These are how the pipeline will be constructed. So the design is the 3D as a virtual reality. So pipe wall position optimization. So after the beam verification, this is a location of refrigerant pipe relocate because the space is not enough. So they reroute it. So it's a relocate. They relocate the pipe, refrigerant pipe. So this is the use of beam. So the other it is to refine slab level. making work ready by coordinating detailed 3D design. So this is by section A and section B. So they will look into the pipework installation in the bathroom by the sunken slab. So rendering from mock-out flat for the interior design. Okay, lifeline experience interior design. So it's have a better collaboration from shared vision of need, value, and purpose in the design phase. So the summary, 4W and 1H. So why you using the BIM? It's a business initiative, time, cost, quality, customer satisfaction, and also as a business challenge, limitation of 2D and collaboration. So what is BIM? BIM is the produce to 3D, 4D, 5D design construction or O&M and safety and go green. So it's a lean construction, VDC asset lifecycle management. So who will be using it is the using and benefit to developer, consultant, contractor, customer, and also BIM consultant. So when is for during the project lifecycle design, build, and OM. So lastly is how. So BIM executed the plan. So that's all for me. Thank you.